Alright, the next data structure we're going to cover is queues. Imagine you're at the checkout line of a grocery store. So blue is the first person in the line. So they're going to walk up to the cashier with their items and they're going to check out. While they're being helped by the cashier, another person lines up in the line with their own items. A little bit after, another person comes in, also lines up right behind green. Since blue was the first person at the checkout line, they are going to be helped first, and then they're going to leave the grocery store. Green is the next person in line, say they will be helped next. They're going to finish, and then they'll leave the grocery store. Next we have red, they get helped, they check out, and they leave the grocery store. This is the principle behind a queue. The first element inserted at the tail/rear of the queue will be the first element to exit the head or front of the queue. This first in, first out behavior is incredibly useful. In real life, you could potentially see it being used in an operating system to schedule processes, such that the first process to arrive is the first to be handled. The operations for a queue consists of in-queue, dequeue, peak, also known as front, and is empty. For in-queue, you're adding an element to the rear of the queue, and you have a constant time complexity. For the dequeue operation, you're removing the element from the front of the queue, and it once again has a constant time complexity. Peak, also known as front, is returning the front element of the queue, once again a constant time complexity, and is empty is checking if the queue is empty. Once again, it has a constant time complexity. Constant time complexity meaning that regardless of the input size or how big your queue is, whether it's one element or a million elements, the time it takes for an operation to complete is going to be the same. Alright, before we continue talking about queues, I want to cover modulo operators really quickly because we're going to need it in a little bit. So a modulo operator, often shown as a percentage sign, finds the remainder after division. So in this case we have 17 mod 5 gives us a remainder of 2. One way you can think about this is in terms of cookies. Let's say you have 17 cookies and you have bags that can hold at most 5 cookies. You want to see how many cookies are left after filling as many bags as possible, right? So we take our first bag, we fill in 5 cookies. That leaves us with 12 cookies, so that means we have enough to fill another bag. We fill in another 5 cookies. We're left with 7 cookies. That means we have enough to fill another bag. We're left with 2 cookies. 2 cookies isn't enough to fill a whole bag, so that means 17 mod 5 leaves us with 2. Another way you can think about this is through the use of a clock. Imagine that it's currently 9 o'clock, right? It's currently 9 o'clock. And you know that you need to see your friend in 6 hours. So 9 plus 6 equals 15. But our clock only goes up to a maximum of 12. So what does 15 hours really mean? Well, let's see. If we were to go 6 extra hours to 10, 11, 12, 1, 2, 3, we get to 3 o'clock. Well, this is essentially what the mod is saying. 15 mod 12 gives us 3. It's essentially telling you where you will land after you wrap around a certain number. That certain number being 12, we took 1, 2, 3 steps. One way that we could implement a queue is through an array. And if we have an array, it means that we have a fixed size. So in this example, our array has a capacity of 3. And as well as our array, we are going to be using a front and a rear variable to keep track of which index we're at for the front and the rear. The reason we covered modulo previously is because we need to use the modulo operator to determine the front index as well as the rear index. Initially, they're both going to be pointing to -1, so we're outside of the array. Let's say we wanted to enqueue x. What would we do? Well, we would do -1 plus 1 modulo 3, which is going to give us 0. Same thing for rear. We're going to do -1 plus 1 modulo 3. Now we're doing it for both of them right now because currently they're both pointing outside. In other scenarios, we wouldn't move both of them, but we'll get to that in the example, right? So we're no longer pointing there. We are going to be pointing over here, and rear is also going to be pointing to index 0. And now we can finally insert x. We want to enqueue y. We would now, since front and rear are no longer pointing to -1, we would now only be concerned with rear for enqueue, right? So rear is currently pointing at 0. 0 plus 1 modulo 3 is going to give us 1. So we're going to update rear to point to index 1, and we're going to insert y. We want to enqueue z. Once again, we look at rear. We're currently at index 1 plus 1 mod 3 is going to give us 2. So move rear to point to 2, and let's insert z. What happens when we do peak? Well, we go to front. We see that we're pointing at index 0, and the value is x. So we would return x. What happens if we did dequeue? Well, we go to front, we'd see that we're at index 0, the value is x, so first let's temporarily save x, right? Let's clear that out in the array, and then we need to update where front is pointing to. So it's currently pointing at 0, but we're going to increment it by 1, mod it by 3. That's going to give us index 1. So now front is pointing at y. What happens when we do another DQ. We see front pointing at index 1. It's pointing to Y, so temporarily store Y. So we can return it at the very end. We're going to clear out Y. We are going to update what front is pointing to. So it would be 1, index 1 plus 1 mod 3 is going to give us 2. So front is now pointing to index 2. But what happens now? Oh, and then you would obviously return Y after you're done. Let's say you want to now enqueue B. What would you do? You would look at rear. Rear is currently pointing to index 2 plus 1 mod 3 is going to give you 0. So you would update rear to point to index 0, and you could insert B. Let's try a few more DQs. If you did DQ again, you would see that front is pointing to index 2, and the value is currently Z, so let's temporarily store that. Let's clear it out in the array, and let's update front. Front is at 2 plus 1 modulo 3 is going to give us 0. So we're currently pointing, sorry for the poor arrow, it's pointing at index 0. And let's do one more DQ. If you did DQ, you would go to front, right? You would see that it's pointing at index 0, temporarily store what it's pointing at, B, clear it out. And this time, instead of moving front, since front and rear are both pointing at the same index, that means that we are now empty. Our queue is empty. So what we would do instead is, instead of incrementing it and using the modulo operator, we would simply point front and rear back to -1. Alright, let's look at the implementation for a fixed size queue using a circular array. So for our constructor, we are going to pass in the capacity to initialize the size of our array. We are going to have front and rear both point to -1, so they're outside a valid index. And then we're going to have n as the capacity of our queue. For enqueue, we have the value that we want to enqueue into the queue. We're going to check, is our queue full? If yes, raise an exception. If the queue is empty, then update front and rear to be pointing at 0. Otherwise, you would go into the situation where front and rear are already pointing to valid indexes, and then you can just increment rear by 1 and use the modulo operator to make sure it's at the correct index, right? So you have a valid front and rear. you're going to set the value at index rear to be equal to the value that we passed into the method, right? You have your DQ method. You're going to check, is your queue empty? If it is, raise an exception. Otherwise, save the current value at the front, then clear it out, and then check. If your front and rear indexes are equal to each other, that means your array or your queue is now empty, in which case set their values to -1, right? If you're not empty, then you simply would push front to the next valid index, right, using the modulo operator. Finally, you would return that value that you saved. Next, we have the peak method. You are going to check if your queue is empty, raise an exception. Otherwise, return the value at the front index. We move on to the isEmpty method. If your front and rear index are both pointing at -1, that means your queue is empty. If you were to increment rear by 1, and that would result in the same index as front, that means your queue is full. The previous implementation using an array is great, but it does have the limitation of having a fixed size. How do we get around this? By using linked lists, right? That's how we can implement a dynamic size queue. So what we're going to do is we're going to use a double linked list, right? So over here we have two sentinel nodes. We have the head node and the tail node. These are going to be the gatekeepers. These are always going to be present in our queue, whether we are empty or whether we have a million nodes, right? So right now, head is pointing with the green line. Its next is going to be tail. And tail is pointing with the purple line as its previous to head, right? So if we did is empty here, it's going to evaluate to be true because we see that if we go to the head sentinel node, it's pointing to the tail sentinel node as the next. So what about if we do in queue X? The first thing we're going to do is we are going to create that node, X, fill the data with X. Then we are going to go to tail. We are going to go to previous, the previous node, and that's what we're going to set the previous for our new node. So previous is going to point to head. Then we are going to set the next for our new node as tail, right? We are going to go to tail. We're going to look at its previous value, the previous node in the sequence, its head. We are going to set next for this node to be the new node that we've created. So it's going to point over here. And tail, its previous, is now going to point to our new node. So it's going to point here, right? Let's try a few more examples to get this in. We do in queue Y. What do? We create this new node, set the data to be y. We are going to go to tail, look at previous, see that it's pointing to x, and that's what the previous node is going to be for our new node. Right? The next value for our new node is always going to be tail. Right? And then we're going to go look at tail, look at the previous node, it's x, and we're going to update next for x to point to our new node. So it's no longer pointing there, it's pointing over here. We are going to update tail to point its previous pointer to our new node. Right? Let's try it one more time. We did in Q Z. Create that new node, set the data to be Z. Then you are going to look at tail. It's pointing to previous node Y. That's what you're going to set your new node's previous as. We are going to then go to set the next for our new node to be tail. We're going to go to tail, the previous node. We're going to set this node's next as our new node. And we are going to set the previous for tail to be our new node. All right, let's try to do a peek operation. What we're going to do is we're going to go to head. We're going to go to the next node that it points to, which is x, and that's the value that we're going to return. What happens if we do a dequeue operation? We are going to go to head. The next node that it points to is x. We're going to save that value to return, right? We're going to look at the next node that it points to, which is y. That is what we're going to have head point to instead of x, right? And we are also going to have y, instead of pointing to previous as x, we're going to have its previous point to head. And then we can treat x as if it no longer exists, and then we can finally return the value x. Let's do a few more. We do dequeue. Once again, we go to head. The next node that it's pointing to is y. So let's save that. Y's next value, or next node, is z. So we're going to update head to now point to z. and then we're going to have Z, instead of pointing to Y, we're going to have Z point to head, because we always know we always have access to head and tail. Right? And then we can treat Y as if it no longer exists, and then we can return the Y value. One more time, if we do TQ, we go to head, it points to Z. The next node that it's pointing to is tail. So we want head to point to tail as this next. For Z, its next value is tail. Instead of having its previous point to Z, we want this node to point to head. Right? One thing I forgot was to store the value of Z. Right? Then we can treat this node as if it doesn't exist, and finally return Z. At this point, our queue is empty, but our sentinel nodes still exist, and they point to each other. Let's look at the implementation for a dynamic size queue using double linked lists. So we have a class for node. The constructor in it is going to pass the value is defaulted to 0, as well as the next pointer defaulted to none, and the previous pointer defaulted to none. For our queue, our constructor is going to consist of our head node, our head sentinel node, our tail sentinel node, and then the next for head is going to be tail, and then the previous for tail is going to be head, right? If we in queue, we are passing in the value, that's what our new node's data is going to hold, and then the previous node is going to be what the previous node for tail is, and then the next node for the next for our new node is going to be tail, and then we go to tail, the previous node that it's looking at, that node, its next node is going to point now to our new node, right? We are then going to go to tail, and we're going to set its previous to be equal to our new node. For DQ, we're going to check if our queue is empty. If it is, raise an exception. Otherwise, go to head, the next node after head. That's the node to be removed. You're going to save the value for that node as top value. You're going to go to head.next, and now instead of it pointing to this node, it's going to point to the next node after that, right? And then that same node that we just talked about, its previous value is going to be set to head, right? Finally, you're going to return top value. For peak, you're going to check, is your queue empty? If it is, raise an exception. Otherwise, simply return the next node after head's value. To check if your queue is empty, you're simply going to see if the next node after head is equal to your tail. While it's good to know how to implement a queue from scratch, many programming languages have a built-in queue or a queue library. For Python, you would do an import from collections. You would initialize the queue using the dequeue method. Then the in-queue equivalent would be append. So over here we're enqueuing A, then we're enqueuing B, and then we're enqueuing C. If we wanted to peek at the head element in the queue, you would simply look at index 0. If you wanted to dequeue the head element, then you would do pop left. If you wanted to check if the queue was empty, you would see if the length of the queue is equal to 0. So that's a wrap for queues. So after this video, you should be able to describe a queue / a first in, first out collection and its operations. You should be able to implement a fixed size queue using an array. You should be able to implement a dynamic size queue using a linked list. You should be able to compare the two implementations and understand the time complexity for the operations. Next, we are going to be going over hash maps.